This is the third section for week 3 of Astronomy 3010. And so for this section we're going to talk about different shapes of orbits and whether orbits are bound or unbound. And this can be thought of as being conic sections. What I mean by that is that if you take a cone, as we have down here, and you slice through it, you can either get a circle if you cut straight across parallel to the bottom, and get an ellipse if you cut an angle parallel to the not parallel to the bottom. You can get a parabola if you cut down at an angle but intersect the bottom, and you can get an hyperbola if you cut down but you are going slantways almost parallel to the edge. And so what we get is a circle, an ellipse, a parabola, or a hyperbola. And that's the different types of orbits you can get where there is a massive body giving rise to gravity and something coming close to it. So we have two different bound states, that is to say that whatever is coming close to the massive object, in the case of the solar system that would be the sun, it stays in orbit. So you can have a circular orbit or an elliptical orbit. So the sun has a fairly circular orbit around the galaxy. Some planets have fairly circular orbits. All planets have elliptical orbits. They are bound within the solar system. For unbound states, we have parabolic and hyperbolic. And it's basically a factor of how much they're affected by the gravity of the sun. Some comets orbit and come back and have highly elliptical, so they're very eccentric ellipses for orbits. But many of them come in and leave again. They don't stay in the solar system, and they have parabolic or hyperbolic orbits. And so you can think of this as being to do with the energy. If an orbit is unbound if the object has enough energy that it can achieve an infinite separation from the object it should be orbiting. So for a comet on a parabolic orbit, it has energy that will allow it to escape from the sun. And by escape we mean it gets to an infinite distance from the sun. If it has more than enough energy, it's hyperbolic. If it has exactly the right amount of energy, it's parabolic. But if it doesn't have enough energy to escape, then it stays in orbit. It is bound, and then we get circular or elliptical orbits. And so, as I said, if we have exactly balanced energy, that is that the total energy is 0, then we have just enough energy in the object to get it to infinity, and that is a parabolic orbit. So that's quite a special case. So with conservation of energy, TE is the total energy. You have kinetic energy and potential energy. And basically, for a bound orbit, TE is negative. You have a lot less energy than you need to escape. If you have positive energy, then you can escape. You have enough kinetic energy to overcome gravity. But all the time, while you're in orbit, you're exchanging kinetic energy and potential energy. So here we have, this would be, say, for a satellite. We've got the Earth, and we've got a nice elliptical orbit with the Earth at one focus. And so you've got the satellite coming in, it's on an elliptical orbit. As it's coming in, it's being pulled by the Earth, it's accelerating, it is converting potential energy to kinetic energy, it is getting faster and faster and faster until it gets to here, and it will then have enough energy that it can pull away again, and it will pull away, and at this point it is converting kinetic energy to potential energy. It's working against gravity, it's moving away, and it's converting energy until eventually it's got to a point where the potential energy is very high and there's basically no kinetic energy left for it, and so it has to pull back in. So we have this conservation of energy. We have potential energy, which is the work done against the gravitational field and is always negative. And work done is basically force times distance. So we have a force acting on the object that's orbiting, which is given by gravity, so it's F equals gmm over r squared. And so our potential energy, our gravitational potential energy, is just F times r, where r is our radius vector, and so it's gmm over r. Then we have our kinetic energy, which is half mv squared. And so what we have is the total energy is a half mv squared minus the potential energy. And so you can see that if this number is conserved, if you can always have exactly the same amount of energy, then as something moves in towards the Earth, it's being pulled towards the Earth, it gets faster and faster until eventually it can pull away again and it moves out. But as it moves out, it's increasing its potential energy because its distance is getting larger and larger. This number gets smaller and smaller, or more negative, actually. And so this can explain to you how you can get Kepler's second law. Now, let's consider that we have two massive bodies pulling on each other. So, for instance, we have the Moon and the Earth. They are orbiting each other, actually mostly the Moon orbiting the Earth, but they are orbiting the center of gravity of the system, which is inside the Earth. And why, if they're pulling on each other, do they not crash into each other? So I want you to think about what it takes to get into orbit. So here I'm standing way above the Earth, and I drop an object. And as I drop it, it falls directly down towards the center of gravity, so it falls straight down to Earth. But if I throw it with some lateral speed that is perpendicular to the direction towards Earth, then it will still fall down, but it will curve a little first. It will have a parabolic path. If I keep throwing it faster and faster, eventually it will be, so it's not fast enough to get into orbit. It's not fast enough to get into orbit. But from here, I've now got it where it's not going to actually hit the Earth. It's moving at a fast enough rate that it falls around. So it's constantly being pulled towards the Earth, but it's got enough speed to keep going around and around. And so here we've got, it's in circular orbit, and as it's going faster and faster, if I throw it faster, it will move in an elliptical orbit, and that ellipse will get longer and longer the faster I throw it, until eventually it will have enough speed that it won't come back around, and that is escape velocity. So just to kind of summarize that, we have that, it's not so much that they are orbiting each other, but the Moon falls around the Earth. The speed of the Moon is right to mean that it doesn't fall towards the Earth. Its parabolic path is actually slightly flatter than the curvature of the Earth, and so the Moon is always falling towards the Earth, but the Earth moves away from the surface of the Earth is moving away from it. And likewise, the Earth falls around the Sun. Okay, so we have the idea of circular velocity, and this is basically the minimum speed. This is what speed do you have to be in orbit, in a circular orbit. And it is, in fact, just what you need to get an exact balance of the centripetal force and the gravitational force. And so we can get that quite easily. So if you want something to be in orbit, it has to, its speed is given by its distance above the Earth, actually from the center of the Earth, and the mass of the Earth, or the distance from the center of the Sun and the mass of the Sun, and so on. And so that's the speed it must have. If it is moving slower than that, its parabolic path will make it fall back down onto the Earth. Escape velocity is a little trickier, but basically what you have is, this is where you're throwing it fast enough that now it has a parabolic orbit. It has just the right amount of energy so it can get to infinity. It can get an infinite distance from the Earth. It will never fall back down on the Earth. That is the definition of escape velocity. Now remember that the force acting on it is F equals gmm over r squared, and we want to move a small distance dr against this force so that we do work dw. So here we have the work done, this infinitesimal work done is the force times the distance. And so what you then have to do is to integrate. So we want to move from the surface of the Earth, so remember this is the symbol for the Earth, so this is the radius of the Earth, from the surface of the Earth to infinity. So we have to integrate, because every time we move out, r changes. So we have to integrate to get the total amount of work done to get it to infinity. So if we integrate, we get something that looks like this, and then we have to put in the limits. Well, 1 over infinity is 0, and so once we get that in, we have the work done is now gmm over r. So this is the amount of energy that it has to have. So this basically means that you have to have enough kinetic energy that you can use it all up exactly and get to this amount of work done. Okay? So the work done is here. the potential energy is half mv squared over r. Sorry, half mv squared. And so here we just equate them. And if we rearrange it, we get the escape velocity is the square root of 2 gm of r. Remember, this is for the Earth, so I put Earth symbols in. Now, you'll notice that the circular velocity was the same, but without this 2. So, to get something into orbit, you have to get it going with circular velocity. To get it to escape, you only have to go root 2 times faster, which is only about 40% faster. So, the difference between putting something into orbit and making it move too fast so that it can escape are very close together. Now, one thing that I just want to note is that this assumes that it is just a ballistic thing. It's just a projectile. You are throwing it and it has no further thrust. So when you actually send something like a shuttle rocket into space, it is powered. So it never actually has to achieve escape velocity because it doesn't have conserved energy. You are adding to it. You're pushing it constantly. And so that allows you to get out of the atmosphere and into orbit without ever being at escape velocity. And that's it for this section.